Hello everyone. So the next part is the variation of pressure, right? So we have already discussed the definition of pressure, the units of pressure. Now we shall be discussing about the variation of pressure with height or with depth. So the next part is variation of pressure with with depth. So now let us consider here is a container. Suppose it is a container and there is some water or any fluids. So let us say here is a point A, here is a point A, and here is a point B. Okay, let us consider these 2 points, and these 2 points is separated by, let us consider these 2 points is separated by some very small distance, let us say h, or let me put this in way, then this way, let me put this, let us say this is some dz as height or depth is involved. So it is along z axis. We consider that this way. We generally consider this to y axis, this to be x axis, and this to be z axis. So let us consider this, the separation between these 2 points, A point and B point, is very small, which is z, right? The vertical height between A and B is dz. Okay, so imagine here is a surface around B, and let us imagine another surface around A, both of the surface area, let us say delta S. So this is one delta S, that is another delta S. Clear? So now here on this fluid enclosed between these two surfaces, between this two surface, this delta S and that delta S, between this cylinder, right? So we are having a cylinder here. We are having a cylinder here full of fluid. Here this is point B, and here this is point A, and there is some fluid inside this volume. So on this volume, on this fluid enclosed between these two surfaces, this delta S and that delta S, what are the forces acting on it? The forces acting on it, let us say, so suppose this is our cylinder. Okay, let us say a cylinder. This is point A, this is point B. On this surface, here will be a force due to the pressure of the fluid which is above. Pressure is always compresses, so into the cylinder it will compress it, right? So here is some pressure, let us say a force, let us say F2, right, vertically upward, but the fluid above it, and this is vertical downward, sorry, by the fluid above. And here is some other force, let us say F1, and this is exerted on this cylinder by the fluid below this, the fluid here, which is staying here, and it is pushing it upward, trying to compress it. And the other force which is acting here, is that the weight of the cylinder, let us say that W is acting vertically down. So F2 is vertically downward, F1 is vertically upward, and W is vertically downward. So these are the three forces which are acting on the fluid uh, in this cylinder, right? So let the pressure at surface A, this surface, let's say the pressure at this surface is P. let the pressure be at this A surface is P, and here P plus dP. So what is the difference then? dP is the difference, and we need to find out the variation. That is, we need to find out the dP, the relation of dP, which is the pressure difference between point A and point B, and this dz, right? So the pressure difference is dP, but the difference in height or difference in depth is dz. So we aimed at finding out the relationship of dz with d, right? So how can I write here? Here at this point B, the pressure is P plus dP. So F2 can be written as P plus dP multiplied pressure into surface area, and F1 can be written as pressure at P. So pressure is P and surface area is delta S. So these are the two forces, right? So if there is some vertical equilibrium, so for vertical equilibrium means this cylinder or this volume within surface, within this surface and this surface, if this cylinder does not move vertically, it does not go down, or if it does not go up, then for this vertical equilibrium, all the summation, the sum of all the vertical forces should be 0. So we can see from this thing that F2 is downward, F1 is upward, W is downward. We can say that the F1 is equal to F2 plus W. W is what? Weight of the cylinder, weight of the volume of the fluid inside this cylinder, right? So this F1 can be written as P delta S. F1 can be written as P delta S. F2 can be written as P plus dP delta S, and W can be written as, see, the volume inside this cylinder. W is what? The W can be written as, can be written as the volume multiplied by density, volume multiplied by density multiplied by G. Why? Because this is volume V multiplied by rho. So this is actually M, mass. So mass into G, mg is equal to weight, right? So volume is what? The volume is delta S multiplied by dz, because this is area of cross section and the height. So V is delta S dz, right? Delta S dz. Let us put this within first bracket, and rho is there, rho G. So this is our W. So instead of W, we can write that delta S multiplied by dz multiplied by rho multiplied by V, right? So this is very obvious. So as you can see, this delta S is common everywhere. This delta S is common everywhere. See, here is some delta S, here is some delta S, and here is a delta S. So delta S should be cancelled out. This will be cancelled out. So P is equal to P plus dP plus dz rho G, right? And this PP will cancel each other. As you can see, dP can be written as minus rho G dz. So here we get the relationship of dP and dz. Relationship of dP and dz. See, this is the thing we try to find out. Right? Now, let me, so this negative sign, what does this negative sign mean? So this means as we move up to a height dz, see, if dz is positive, let us say dz is positive, then according to this equation, dP will be negative. Now if dz increases, let us say this is the positive side, This is the positive side of what? dz. Why? Because we are going up along this z axis. So this is the positive z axis direction. So as we move up, as we go from A point to B point, this dz is positive. So as we go up, if this is the positive side of dz, then if dz is positive, dp will be negative. That means if we go up, if we go up, then pressure will what? Pressure will be, the change in pressure will be negative. That means pressure will decrease. Pressure will decrease. If dz is positive, dp will be negative. And what is the positive dz? Positive change in z. That is if we go up. So if we go up, dp will be negative. dp will be negative means pressure will decrease, right? So as we go up, pressure will decrease. As we go down, pressure will increase, right? This we can prove also. How? Through integration, right? So now we consider, suppose here is some point. You consider this point. Let me go back to the initial diagram. Let us say the point at the bottom is having z is equal to 0. Point at the bottom is z is equal to 0. And here is some other point which is where z is equal to h. Let us say this height is h. So this is z is equal to 0, this is z equal to 0. Let us find out the relationship, the definition, sorry, the difference of pressure between these 2 points. So then how to derive this? Let us use this equation. So here let us say this dp is changing, and let us say this assume that here the pressure is P1 and here the pressure is P2, right? So we are going up, this dz, as we are going up, dp is from P1 to P2. See, we are going from, the variation of pressure is from P1 to P2 as we are going up, right? So this dp is equal to, so minus rho, sorry, g, one second, I'm erasing this part, rho g dz, and the z is being varied from 0 to h. So very easy, this dp will be P2 minus P1, and this z will be what? See, this rho is a constant because we are having an ideal fluid. We are considering an ideal fluid, right? Incompressible fluid. So rho will be, the density will be constant. So rho will be coming outside the integration sign. G is a constant. G will be coming out of the integration sign. So it will become 0 to h dz, right? So we get what? We get P2 minus P1 is equal to minus rho g h minus 0, which is minus rho g h. So we can see that P2 is equal to P1 minus rho g h, right? P1 minus rho g h. So what do we see here? That, or we can write that P1 is equal to P2 plus rho g. This is the equation. So as we are going up, by h distance, then pressure is increasing, right? So P2 is lesser than P1, right? P2 is lesser than P1 by the value rho g h, right? So this is the equation that you should remember always. So as we move upward inside the fluid, pressure will decrease by the amount rho g h. What is rho? Rho is the density of the fluid, g is the acceleration due to gravity, and h is the increase or decrease in depth, right? Understood? So I hope you all have understood this, right? One more thing here, I have considered the difference in pressure when we go down or go up vertically. If we move vertically upward or down, what if we horizontally move? If you consider a liquid Suppose same thing, same diagram. Suppose here is a container having some liquid in it, having some fluid in it, right? So if initially in this in the earlier case we have moved downward or upward, vertical displacement with. But what happens if we move horizontally? Suppose here is one point A and here is some another point which is B at the same horizontal level. So AB is a horizontal line. So will there be any difference in pressure? Suppose if I say that the A, pressure at A, will that be different than the pressure at B, or PA will be is equal to PB? So what is the truth? Will is this true or this is true? Let us find out. So in the same case, we shall be like this. Likewise, we shall be considering one surface here and the another surface here. Okay, both of surface area delta S. Then consider the fluid staying inside this volume. So this is also a cylinder, right? So what will be the forces? What will be the forces acting on it? See, the the fluid on this side will be applying, the fluid on this side will be applying force in this direction, right? On this direction. Why? Because this forces will be trying to compress this volume. The pressure always try to compress it, right? And the fluid on this side will try to compress this in this direction. So the fluids will be pressing it from this side in this direction, let us say with force F1. And the fluid on this side, on this side, okay, on this side will be applying force on this direction. Let us say that force is F2, right? And let us say the pressure at A point is PA, pressure at point A, this is, so let us say this is PA, and pressure at point B is, let us say, PB. And what are the other forces acting on it? The forces acting on it is W, vertical force. But what are we talking about? We are talking about the horizontal forces. So in case of horizontal equilibrium, the sum of all the horizontal forces will be 0. So if the fluid remains in equilibrium, right? If the fluid remains in equilibrium in case of horizontal equilibrium, that F1 should be equal to F2 because there is no other horizontal forces, right? So what is F1? Pressure at A multiplied by delta S. What is F2? Because delta is the surface area. What is F2? PB multiplied by delta S. This delta S will cancel each other out. So PA will be PP, right? This is what we are going to find out. So this is not true at all. So this is the correct one, right? So the pressure is same at 2 points in the same horizontal level, right? So here is the conclusion that the pressure is the same. The pressure is the same at any 2 points at the same level in the field, right? At sorry, bus. That's all. Right? Now, one more thing. This is we're talking about for the same kind of fluid. So we shall be looking at some problems where it will be given different fluids, okay, inside a same container. So we are talking this out. We're talking about this point when the fluid we are considering these 2 points. This any 2 points should be inside the same liquid, right? Always remember these 2 points. These 2 points should be inside same liquid, same fluid. Sorry, same fluid. This is here going to remember, right? And this does not depend on the shape of the container. There is another important point. Try to remember it, or it should be remembered that the shape of the container, right, is it's not important. It's not important, right? So I'm giving an example that if so let us say if suppose this is one container, let us say this is some container. Okay, suppose here is some fluid. Okay, suppose here is some fluid. The fluid is here. Now suppose if you have suppose a point A here, a point here at the same horizontal level, suppose if you have B point here at the same horizontal level, you have C point here at the same horizontal level, you have D point here. So as the A, B, C, D are in the same horizontal level, as you can see, PA is equal to PB is equal to PC is equal to PD, the same horizontal level, right? The shape of the container should not matter, right? So one more important thing that sometimes we are asked to ask in examination, that what is the graphical representation? The graphical representation of what? Of this variation. How to represent this in graphically? Right. Suppose, so can you tell me what is the pressure here at the top of the point? Suppose this point is C. So always remember, whenever we consider a point in the open surface, this is the surface which is open. That is, here there is some air, right? There is some air. So this C point is directly connected to air. That means this is one such point, or this is one such point PD, which is in contact with the air. So all the points in the free surface, those who have air above them, will be having same pressure, and that pressure is actually equal to the atmospheric pressure, right? So PC is equal to PD is equal to PE. We consider that to be PATM, atmospheric pressure, or sometimes, or most of the times, we call it P0. So P0 is what? P0 is the atmospheric pressure, right? So if I consider one such case, suppose here is some container and we have some liquid inside. So at the free surface, the pressure is what? The pressure is P0, right? Now if I go down by depth H, so here at some point, if suppose pressure is P dashed, then what will be the value of P dashed? The value of P dash will be P dash is equal to P0 plus rho g H. Why? Because if I go down by H, the depth increases, so that the pressure increases. So the change in pressure will be rho g H. And what was the initial pressure here at this point? P0 at the atmospheric pressure. So at this point, the pressure will be P0 plus rho g H. At this, suppose this height is suppose H1. This height, this depth is suppose H1. So here at this point, the pressure will be P0 plus rho g H1. Rho is what? The density of the liquid. G is the acceleration due to gravity, and H or H1 is the depth of the particular point. So how to consider that? At the bottom, see, the thing we considered, that we have considered this part to be 0, this part to be 0 here. So at z is equal to 0, right, and this part to be the z is equal to h. So if I consider the graph between P and H actually, then how to consider that? That P and Z. Let us say this is P and this is at Z. So at Z is equal to 0, at Z equal to 0, the pressure is the highest one, right? The pressure is what? The highest one. So at this Z is equal to H, when Z is equal to H, suppose Z is equal to, this is equal to H, the pressure is the minimum, which is P0. So let us say the pressure is P0, right? So at P is equal to P0, then it actually decreases, the pressure decreases to P2. So how to draw this graph? How to draw this? Okay, so at H depth, it is P0. At at initially it is at 0 depth, sorry, at 0 depth it is P0. When, suppose, let us say this is depth, this is depth. At 0 depth means at the surface, it is P0. So we are starting from here. Now at H depth, it is P1, right? So this is P0, let us say this is P1. So at H depth, this is P1. And P0, they should be linearly increased. They should linearly increase. And this increase in pressure, this factor, this should be rho g h. Or we can directly say from y is equal to mx plus c formula, right? So P1 can be written as P0 plus rho g h, right? Right. So if I take this to be y-axis, y is equal to mx plus c, right? X is what? This is x. So m is mx plus c. So c should be P0, right? C is P0 here, and what is m? M is equal to rho g here, right? So the slope will be rho g. So this is what should be known about the variation of pressure with height, right? So that is all today. Let's meet in the next class. Thank you.